Hi everyone, today we're going to go over the X-ray Diffraction Lab or XRD lab. XRD is a tool that is used to try to piece together the crystal structure of a sample, which is done by determining the d-spacing between planes from the way that X-rays interact with your sample and are reflected. I know that the XRD is called X-ray diffraction, but it's better to consider the X-rays being reflected rather than diffracted. So in X-ray diffraction, incoming X-rays, two incoming X-rays hit your sample, and depending on the atom arrangement, if it's a crystal structure, it will, and depending on where the atoms are located, will scatter the X-rays in different directions. But the X-rays that are detected and are seen in XRD spectra are those that are reflected. So I hope that makes a bit of sense. But in general, in XRD, there are two incoming X-rays, as I said previously. In here, these incoming X-rays are seen in green, and there's an X-ray denoted as 1 and an X-ray denoted as 2. Now, from the image, we see that X-ray 1 hits basically the first layer of atoms, or the first plane of atoms, and then it's reflected. But the second incoming X-ray, which is denoted as X-ray 2, has to go an extra distance, which we see is highlighted in pink. So we see that black dash line that shows the two incoming X-rays being the same length. We see that right where the first X-ray or X-ray 1 is reflected, but it takes an extra distance, or an extra set of wavelengths, or not wavelengths, but just an extra distance for the second X-ray to then get reflected. Now, this extra distance can be found and is also related to the distance between two planes in a crystal structure. Now, the way that they're related, we can think of it as in more simple terms. If we think of the two incoming X-rays as two parallel lines cut by a transversal, and that transversal, or think of the two planes cut by a transversal, which would be the incoming X-ray, we can see that the theta c, which is the angle at which the X-rays are hitting the sample, is actually the same angle that we see when we take the distance, or d, and then see where it's cut off, or where there's a cutoff, or the difference between the incoming X-ray 1 and X-ray 2. So we see that theta c. So we see here, and we treat this sort of area as a right triangle, we see that we can relate this extra distance by d sine theta c. So I know this is a little confusing, but if we see theta c, which is the angle between the planes and both X-ray 1 and X-ray 2, we see it's the equivalent of the incoming X-ray 2 and the angle between X-ray 2 and the second plane of atoms. And if we denote that as theta c, and we treat this as a right triangle, we know that the angle here would be 90 minus theta c. And then the to basically follow that all angles in a right triangle have to equal 180, then we would see that here this would also be theta c. So then, in order to determine this extra length here, we would only consider then that sine theta is equal to the opposite length over its hypotenuse, which in this right triangle would be d. So basically, this length here, highlighted in pink, would be d sine theta c. Now, in order to consider the entire extra distance that wavelength not only travels, not only as it's hitting your sample, but as it's being reflected, we actually then take into account this other equation, which is n theta equals 2d sine theta c, which accounts not only the length of the incoming X-ray 2 as it's hitting your sample, but also the length of that it has to travel to when it's reflected on the plane, the second plane. And this is known as Bragg's angle. And so this sort of tells you, not only tells you, can help you determine not only tells you, but it helps you determine the distance between two planes. But there is something to consider when looking at an X-ray or XRD spectra. Now, if this distance of the second X-ray allows for both X-ray 1 and X-ray 2 to be in constructive interference, that means that the peak of X-ray 1 and the peak of X-ray 2 as they're being reflected are in the same location, then that would lead to constructive interference and X-ray intensity that can be detected. And at this X-ray intensity, a high enough X-ray intensity, we would then see a peak at some theta c, or some corresponding theta c. So then, but if there was a case where this extra length causes there to be sort of a shift in the waves, so that there's deconstructive interference, where basically instead of having a peak meeting with a peak and a trough meeting with a trough at the same location for both X-ray 1 and X-ray 2, then there's a trough where there's a peak, then that would cause some interference and we would get no signal basically, and there would not be a corresponding peak at that theta c. And basically, just depending on how the atoms are arranged and their d-spacing, this sort of affects whether we see a peak, or whether it basically affects the X-ray intensity to either see a peak or not see a peak. And so then this is more, I guess, more evident for when we do XRD, where there's an X-ray source and an X-ray detector. Now, as you see here, this 2 theta is the diffraction angle, which is usually what you would see in a spectra in the X axis. And then the Bragg's angle is the angle relative to your sample and the X-ray source, so the incoming X-ray source. Now, this 2 theta, we saw that it's basically the angle of the incoming X-ray, and basically this is the incoming X-ray, and then to the X-ray detector, which would be 2 theta. Now, and basically the theta would be the Bragg's angle. Now, for certain crystal structures, they have different arrangement of atoms. And so, for example, for BCC, if we have HKL, which are representative of a plane, if we have the HKL of a BCC, if we have the sum of these Miller indices for the plane to be odd, then there would not be a diffraction, or we would not see, basically detect a peak for that particular distance or that particular plane. And so there's the same thing, but if all the Miller indices for that plane, if the sum is even, then we would see a diffraction, or we would see a peak for that plane. And so then that makes sense, because it depends on the extra distance at the second incoming X-ray it has to travel for there to be either constructive or deconstructive interference. And for FCC, it would be that if there is both odd and even HKL numbers, then you would not see, for a plane, let's say that would be like a 3-2-1 plane, then you would not see, there wouldn't be diffraction. And the same thing would be for for unmixed, where if you get either a 1-1 plane or a 2-0-0, you would get some sort of diffraction to occur. And then HCP, or hexagonal closed pack, would require that the H and 2K equal a 3N, and that L be an odd number. And then all other cases would be that we would get diffraction. And so then this sort of, so then it says here that the first order diffraction, or n equal to 1, of a given H scale reflecting plane is usually given more importance because it is of higher intensity than the corresponding higher orders or their harmonics. So it's usually the first order. So basically, some of the so this is due to the fact that the intensity of X-ray diffraction fall off rather than drastically with the 2 theta. So if the higher order reflection actually exists, why are they often weaker? This has to do with the interference. So we kind of talked about that before, that electrons in an atom that diffract X-rays are not all in the same spot. And at higher 2 theta angles, the diffraction from different parts of the electron cloud are showing destructive interference. So again, this could be due to the way, the distance or how far the second incoming X-ray is traveling, so that the waves don't longer meet in a way that there's constructive interference. But that can also be the way that the X-ray interacts with just the sample or the crystal structure as a whole. So in general, the X-rays are being scattered, but think of it as being reflected. Now, scatter in many directions won't actually, even though the X-rays are being scattered, won't actually necessarily give you the reflection you need so that it's detected by the detector, for lack of a better word, and for you to get a peak there. And that depends on many factors, and some of them depends on the way that, and obviously that depends on how the atoms are arranged, but also in part of the, and also can be, in part because of the electron cloud and how it shows the destructive interference. Now, if you have a photon with a wavelength lambda, then you have only one lambda. And the relationship is valid also with any multiple of this wavelengths, but mathematics has to be matched with physics. Now, the example here is that if HKL were to be a 200 plane, then you can interpret this like if you were to get a peak at a certain 2 theta that you think corresponds to 200 plane, it can also be plane 100 with a second order diffraction. That means that n would equal to 2. And then, or it can be the 200 plane, but with a first order diffraction with n equals to 1. And if we were to plug this in into Bragg's equation, then we would see that we would get the same angle for both cases. So technically, the 2 theta position can give you 2 possible scenarios. Okay, for the first example that we're going to work out today, it says the mineral perovskite, calcium titanate, occurs naturally together with rare earth impurities, and as such is an economically significant source of several rare earth elements. In pure form, it is a useful material which to make electrical insulators, and it also has many other interesting properties. Attempts to produce synthetic calcium titanate are often thwarted by the simultaneous formation of other oxide products, such as the following. Experiments performed on the products of one particular synthesis experiment gave the following powder diffraction results when X-rays with wavelength of 0.1542 were used. So as we see here, so there's different formations of this calcium titanate. The desired one is the calcium or the CaTiO3, but obviously there's different oxides that can form. So we have the following information, which basically gives us all the peaks that we're seeing, all the different 2 theta peaks, and then we are given the relative intensity, and we are given some of the despacings. So for the first part, it says an experiment performed on the products of a particular synthesis experiments give the following powder diffraction results when X-rays with a wavelength of 0.1542 nanometers were used. So we have the wavelength, and it says calculate the missing D spacing using Bragg's law. So to calculate theta for the missing D, then we have to calculate the D. So basically everything is given, right? So we are given all the thetas that we need to calculate for, which are 33 degrees, 33.17, and 33.33. So we can use D equals lambda 2 sine theta, where lambda in this case is 0.1542. And we know, so we basically know that this is the wavelength that's used, and we have these two thetas, so we need to account for just theta. So we basically use this 2 theta and divide it by 2 to then plug here as a theta. And then with that, we should be able to find the D spacing, which is found the following. And so comparing to our answers, we see that as we are increasing the 2 theta, the D, it's corresponding basically to a smaller D spacing, and that sort of follows the trend here. So for the second part of this question, it says the data are given from cards in the powder diffraction file using the measured values of D and I from part 1.1. Determine which oxide compounds are present in the synthetic product. So apparently the product is composed of more than one type of calcium titanate oxide. So I guess this is a table, and it gives you the D or the D spacings and the I, or the relative intensity. And basically relative intensity, if we would consider, for example, basically the 100 would be the highest peak in the spectra. And then, for example, one denoted as 60 would be that it's sort of 60% of that highest peak. And then something with a relative intensity of 8 is basically a really small peak. I mean, 4 is even smaller. So relative to 100, it would be like 4% of that 100. So it would be like basically, you would think of a peak, to make it easy, a peak of 1,000 would be the 100 peak, and then a peak with a relative intensity of 4 would be basically 40. And so when we see our spectra, which is the one on the bottom with the different D spacings and the relative intensity, and then compared to the powder diffraction files, we compare basically one by one, and we see that the D spacing of 0.3813 relatively matches that one of CaTiO3. Ours is 58 for relative intensity, and the one for CaTiO3 is 60. And then the next one would be the 0.3405, which the only D spacing, or the only sample that has that D spacing or close to that D spacing, again, is CaTiO3, and its relative intensity is 40. And for the sample that we've calculated for, it's 42, so it's really close. The second one is 0.2979, and we see that that one's not present in CaTiO3, but it is present Ti2O4, though the relative intensity is a little higher for that sample. This one's a little lower. And then the next peak would be the 0.2856, which has a relative intensity of 17. And for that one of CaTi2O4, it's also present there, which is not present in CaTiO3. And then 0.742, it's present in CaTiO2, Ti2O4, sorry, and it has a higher intensity. So if we just see relative intensity, like in our sample, the one that has the highest is at 0.2742, which is the same thing for this. And now the next d-spacing to look at is 0.715, which is present in CaTiO3. And then so forth. We have 0.2701, which has a relative intensity of 100. And then 0.2689, again, is present in CaTiO3 at 80. And so the relative intensity is very close to that sample. And then 0.2564 is present also in CaTiO3. So we see that mainly our sample has all corresponding peaks and with really close relative intensity to CaTiO3, but it also has peaks of Ti2O4. So it might be composed of both of these different calcium titanates. And so we see here that you use only D and compare with the previous table. So we basically see and we compare just the presence of having those planes with that. Okay, so for example 3, we're going to draw some projections, and we're going to do it on 3 types of cubic unit cells as viewed from the 0, 0, -1 crystal vector. And then we're going to label each atom with its C point coordinate, and then represent our plans in a 2 by 2 by 1 grid of unit cells, and then draw the traces of the 1, 0, 0 and the 1, 1, 0 plane on each plan, and then use your diagrams to explain why BCC material cannot give rise to 1, 0, 0 family reflections in their X-ray diffraction patterns, and why FCC cannot give rise to either 1, 0, 0 or 1, 1, 0 reflections. Note that you now have a convenient tool for counting the number of lattice points. The general rules of the systematic absences due to lattice types can be stated as follows. So we know that primitive cells don't have any restrictions to where we can see reflections between planes for incoming X-rays. However, BCC, we know that the sum of the HKL for a plane has to be even, and therefore no reflection will occur if the sum of HKL is odd. For face-centered cubic, reflection of X-rays will occur for planes that are either all odd or all even, meaning the HKL has to be all odd or all even. However, if that's not the case, we will not be able to see. So we consider like the XY plane, and we assume that the Z is coming out of the board. And so then if we go the 2 by 2 by 1 grid, we can assume that if we were to view this from the Z axis, then we would see basically 2 atoms on the Y axis and 2 atoms along, so 2 atoms by 2 atoms, 2 along the Y axis and 2 along the the Y axis would give you basically this arrangement of atoms, which would be 4 atoms if we look from on top or by the XY plane, assuming that there's and then 1 layer in the Z axis. So we would get something like this, right? Then once we have the 2 by 2 by 1 grid unit at the unit cells, we label each atom the Z point coordinate. So where are they located with respect to the Z direction? And we see that the entire layer is basically up 1 in the Z direction. And now we draw planes. We draw one, the first one at the 1, 0, 0 direction, meaning that we move along the X direction by 1. We don't move along the Y and X axis. But in general, if we were to locate the plane HKL with 1, 0, 0, we would find the inverse of the plane. So that means that X is 1 over 1, which is 1 over, and then Y is 1 over 0, which is infinity. So the plane has to basically touch the Y-axis infinitely, and also the L is 0, so the Z axis is 1 over 0, so it always indefinitely has to touch the Z axis. So it looks something like this, where the plane at the 1, 0, 0, if we were to draw, is always on the Z axis, and if we were to draw lines going down, but since it's coming towards us, it would the axis will always be touching also the Z and the Y axis, basically, and it's 1 over in the X direction. So it's 1 over in the X direction, and infinitely touching the Y axis, infinitely touching the Z axis. So it looks something like that. So if you were to draw a family of 1, 0, 0 planes, that's how it will look. So the same goes with the 1, 1, 0 plane. So if we, to locate the plane at 1, 1, 0, we would find the inverse, and the X direction has to be 1 over 1. So that means we, in the X direction, we move by 1, and then the Y would be 1 over K, which is 1 over 1, which would also be 1. And then Z is 0, the L is 0, so Z is 1 over 0, which would be infinity. So it would be infinitely touching the Z axis, but if we were to see the X and Y plane, it would basically be a line crossing over Z and, not Z, X and Y over by 1. So we move along the Y axis by 1 and the X axis by 1, and then have the plane be basically either parallel to the Z axis or always touching the Z axis in every direction. And so we draw a family of 1, 1, 0 planes that looks like that. And so there's not really any interference that would occur with this arrangement of atoms if we were to bring an incident X-ray and have it reflect on these planes, both in the 1, 0, 0 and in the 1, 1, 0 plane. So if we were to do the same thing, and so if we were to draw the 2 by 2 by 1 grid unit cell with C point coordinate, we would see that it has the same as the simple cubic, but it also includes the body-centered atom, I guess, or this atom at the center of the cube, which is denoted as 1/2. And if we draw the planes at the 1, 0, 0, and again, we locate that plane by finding the inverse of the planes, which is 1 over the Miller indices. And we basically see that it is 1 over in the X directions, similar to that of the simple cubic. But unlike simple cubic, the family of planes for the 1, 0, 0 also includes this plane at the 2, 0, 0, and obviously there's a plane at the 0, 0, 0. Now, this is basically the family of planes for BCC. Now, in order for BCC to see some diffraction spectra for these planes, the plane sum of H, K, and L have to equal an even number. And now for 1, 0, 0, that's not the case. And we see that the distances of the interatomic distances, the distances between the planes are about 1/2, which can affect the way that the distance or the n lambda are not an integer. So this can lead to interference, and thus the interference leads to deconstructive interactions with the incoming waves and the reflective waves, leading to no diffraction pattern. However, when we do the families of the 1, 1, 0 planes, we see that the distance is bigger than 1/2 and can potentially be an integer of 1 and can lead to diffraction patterns. So it satisfies the rule that the sum of h, k, and l have to equal an even number. And therefore we see a diffraction pattern for this plane, or these distance, or these d-spacings of the 1, 1, 0 planes. Now for FCC, you have the same as a simple cubic, but you also have 4 atoms. If we see the 2 by 2 by 1 grid unit cell at 1/2 for each of the face center atoms. Now, in order to see some diffraction or reflection of the incoming X-rays, the H, K, and L have to either be all odd or all even. So when we draw or locate the planes for the 1, 0, 0 plane and all their families, we see that they can potentially lead to non or deconstructive interference, which doesn't lead to any diffraction patterns for the 1, 0, 0. And the same goes for the 1, 1, 0 plane. The 1, 0, 0 and the 1, 1, 0 plane both do not diffract. So thank you for your attention and have a good day.